Welcome to our channel, where we bring you the most interesting and informative content from around the world. The Sun, a blazing ball of plasma, dominates our solar system. It is a massive, glowing sphere of hot gases, primarily hydrogen and helium, undergoing constant nuclear reactions. These reactions release an immense amount of energy, which radiates outwards and reaches every corner of our solar system. Its immense gravity holds planets in orbit, dictating their paths through the cosmos. The Sun's gravitational pull is so strong that it keeps all the planets, from the tiny Mercury to the distant Neptune, in their elliptical orbits. This gravitational force also influences comets, asteroids, and other celestial bodies, ensuring the stability of our solar system. The Sun's energy, born from nuclear fusion in its core, bathes our planet in light and warmth. In the core, hydrogen atoms fuse to form helium, releasing energy in the process. This energy travels through the layers of the Sun, eventually reaching the surface and radiating out into space as sunlight. This sunlight is essential for life on Earth, providing the energy needed for photosynthesis in plants and influencing weather patterns and climates. Life on Earth, in all its diversity and wonder, is a testament to the Sun's power. From the smallest microorganisms to the largest mammals, every living being depends on the Sun's energy. Plants convert sunlight into chemical energy through photosynthesis, forming the base of the food chain. Animals, including humans, rely on plants and other organisms for sustenance. The Sun's energy drives the water cycle, supports ecosystems, and shapes the environment in which we live. Understanding our star is crucial to understanding our place in the universe. By studying the Sun, astronomers gain insights into the processes that govern other stars and planetary systems. Observations of solar activity, such as sunspots and solar flares, help us understand space weather and its impact on Earth. The Sun's life cycle, from its formation to its eventual demise, provides a glimpse into the future of our solar system. As we continue to explore and learn about our star, we deepen our knowledge of the cosmos and our place within it. Density, a fundamental concept in physics, describes how much mass is packed into a given space. It is a measure of how tightly matter is crammed together. The formula for density is mass divided by volume, which gives us a clear understanding of how much matter exists in a specific area. Imagine two objects of the same size, a bowling ball and a beach ball. At first glance, they might seem similar because they occupy the same amount of space. However, when you pick them up, the difference becomes apparent. The bowling ball, heavier and denser, has more mass crammed into its volume. This is because it is made of a denser material, which means the particles that make up the bowling ball are packed more closely together. In contrast, the beach ball is much lighter because it is filled with air, which has a much lower density. Density helps us understand the composition and behavior of objects, from the smallest particles to the largest stars. In a laboratory, scientists analyze the density of various materials to determine their properties and potential uses. For example, understanding the density of metals can help in the creation of stronger and lighter alloys. In astronomy, density plays a crucial role in understanding the life cycle of stars. Stars with higher densities can collapse into black holes, while those with lower densities might become white dwarfs or neutron stars. The concept of density is not just limited to physical objects, it also applies to other fields such as population density in geography, which helps us understand how people are distributed across different regions. By studying density, we gain insights into the fundamental nature of matter and the universe itself. The Sun's average density is surprisingly low, only slightly denser than water. This might seem counterintuitive, given its massive size and gravitational pull. However, the Sun's density varies dramatically from its core to its outer layers. The core is incredibly dense, while the outer layers are more diffuse, resulting in a relatively low average density. The Sun is not a uniform ball of fire but a complex structure with distinct layers. Each layer possesses unique characteristics, including temperature, pressure, and density. These layers, from the core to the photosphere, reveal the dynamic processes at play within our star. The core, the Sun's dense powerhouse. At the Sun's heart lies the core, a region of unimaginable density and pressure. Here, temperatures soar to millions of degrees, providing the perfect environment for nuclear fusion. Hydrogen atoms fuse into helium, releasing the energy that powers the Sun. The core's immense density is crucial for maintaining this fusion reaction. This central region extends to about 20% of the Sun's radius and is the hottest part of the Sun, with temperatures reaching around 15 million degrees Celsius, 27 million degrees Fahrenheit. The core's density is about 150 grams per cubic centimeter, g/cm superscript 3, which is essential for sustaining the fusion reactions. The immense gravitational pressure in the core ensures that hydrogen nuclei are forced close enough together to overcome their natural repulsion and fuse into helium. This fusion process releases an enormous amount of energy, which gradually moves outward through the Sun's layers, eventually reaching the surface and radiating into space as sunlight. The core's role is fundamental to the Sun's ability to support life in the solar system. The radiative zone, a dense labyrinth of light. Surrounding the core is the radiative zone. A dense region where energy slowly travels outward. Photons, particles of light, bounce from atom to atom, carrying energy through this dense plasma. The radiative zone's density slows the outward flow of energy, taking thousands of years for photons to escape. This zone extends from the core to about 70% of the Sun's radius and is packed with ionized hydrogen and helium atoms, forming a plasma. The photons generated in the core undergo countless interactions, being absorbed and re-emitted by particles, which significantly delays their journey outward. The temperature in the radiative zone decreases from around 15 million degrees Celsius near the core to about 2 million degrees Celsius at the outer edge. This gradual temperature drop is crucial for the energy transfer process. The convective zone, where density drives solar weather. Above the radiative zone lies the convective zone, where the Sun's density decreases. Here, hot plasma rises, cools, and sinks, creating a churning motion. This convection process, driven by density differences, transports energy to the Sun's surface, manifesting as solar flares and sunspots. In this zone, the temperature ranges from approximately 2 million degrees Celsius at the base to around 5,500 degrees Celsius near the surface. The convective zone is characterized by turbulent convection currents, similar to boiling water, where hot plasma rises towards the surface, cools, and then sinks back down to be reheated. This constant movement of plasma creates a dynamic environment that contributes to the Sun's magnetic activity. The interactions between the convective motions and the Sun's magnetic field lead to the formation of sunspots, solar flares, and other solar phenomena. The photosphere, a glimmer of the Sun's density. The photosphere, the Sun's visible surface, is a thin layer of relatively low density. This is the layer we see from Earth, radiating light and heat into space. Although the photosphere is less dense than the Sun's interior, it still plays a crucial role in shaping our solar system. This layer is about 400 kilometers thick and has temperatures ranging from approximately 4,400 to 6,600 degrees Celsius, 7,952 to 11,912 degrees Fahrenheit. The density of the photosphere is about 0.0003 kilograms per cubic meter, kg/m superscript 3, much lower than the inner layers of the Sun. Despite its lower density, the photosphere is where most of the Sun's visible light is emitted, making it crucial for the solar radiation that reaches Earth. The photosphere is also home to various solar phenomena, such as sunspots and granules, which are convection cells of plasma. Unlocking the secrets of the Sun. Understanding the Sun's density is crucial for scientists studying stellar evolution. By analyzing the Sun's density profile, researchers can model its internal structure and processes. These models provide insights into the Sun's past, present, and future, helping us predict its lifespan and eventual fate. Density, a key to stellar evolution. The sun's density is not static but changes over time. As the sun ages, its core contracts and becomes denser, increasing the rate of nuclear fusion. This gradual change in density affects the sun's luminosity, temperature, and size, ultimately determining its evolution as a star. Conclusion: the sun's density, a window into the cosmos. The sun's density, a seemingly simple concept, reveals a universe of complexity within our star. When we talk about density, we refer to the mass of the sun packed into a given volume. This fundamental property is not uniform throughout the sun, it varies dramatically from the core to the outer layers. The core, where nuclear fusion occurs, is incredibly dense, with pressures and temperatures so extreme that hydrogen atoms fuse to form helium, releasing immense amounts of energy. This energy then travels outward, through the radiative and convective zones, each with its own unique density and characteristics. From the unimaginable density of its core to the diffuse layers of its atmosphere, density plays a crucial role in shaping the sun's behavior. The core's density is about 150 times that of water, making it the most compact region. As we move outward, the density decreases, with the outer layers being much less dense. This gradient in density affects how energy is transported from the core to the surface, influencing phenomena such as solar flares and sunspots. The convective zone, for instance, is where hot plasma rises and cooler plasma sinks, creating a dynamic environment that drives solar activity. By studying the sun's density, we gain a deeper understanding of stellar evolution, the processes that drive our star, and our place in the vast cosmos. Density is a key factor in the life cycle of stars, influencing their formation, stability, and eventual demise. For astronomers, measuring and modeling the sun's density provides insights into the fundamental physics of stars. It helps us predict solar behavior, understand the impact of solar activity on space weather, and even informs our search for exoplanets. In essence, the sun's density is not just a number, it's a window into the intricate workings of the universe, offering clues about the past, present, and future of our cosmic neighborhood. Thanks for watching. Don't forget to subscribe, like, comment and share.